Okay, great. So today's topic is training of neural networks. We have looked at some preliminary ways of training neural networks. Today we'll look at some advanced ways of training neural networks. These slides have been prepared by Parth and myself. I'm Amit Sethi. And the associated tutorial, we will club the tutorial from the previous module and this module. They are quite related anyway, and that has been prepared by um, Mr. Shamsi and Sudhakar. Okay. So let's look at the learning objectives. So by end of this topic, you should be able to write about different ways of initializing weights. You should be able to list issues with vanilla, that means regular gradient descent. You should know how to add momentum to gradient descent. And you will also know about some more advanced optimizers such as Adam, and also some tips and tricks to make the training better to increase the accuracy, including dropout and batch normalization. Okay. These methods are quite useful in deep learning, but since we just taught neural networks, and let's say if you are working with slightly larger neural networks, these topics are general enough that they will help you in that also. So let's get into the presentation. So there will be three parts. The first part will be weight initialization. Second part will be making gradient descent faster. That means you will be able to find the desired solution a little bit faster, and then helping the neural networks train better. Okay. So let's first look at weight initialization. So if you look at this particular neural network, right, these are your input nodes, right? These are your input neurons. These are your output neurons. So what decides your input neurons? What decides how many input neurons you will have? Basically, how many inputs you have in the given data, right? So if you have three-dimensional data, then you have three neurons. If you have four-dimensional data, then you have four neurons. Then what decides your output neurons? Right. So the input neurons, or the number of features decide the input neurons. Output neurons are decided by the number of outputs that you want. So let's say if you are doing n class classification, then you will have n output neurons. If you are doing n vectored regression, then you will have n neurons. Okay. So it is dependent on the output that you want from the neural network. The middle layer, the hidden layer, the number of neurons there, you decide on your own. That's your hyperparameter. And including the number of hidden layers also is decided by you. That is also a hyperparameter. So if you want to start doing gradient descent, what you want to be able to do is start from an arbitrary set of weights and then converge to the set of weights that will give you a minimum. So let me start uh, let me start a blank PowerPoint so that I can type things. I can draw things rather. Okay, so when we draw this optimization curve, right? So what is this x-axis representative of? It's representative of your weights. What is the y-axis representative of? This is basically loss for the given weights. Okay. So if you change the weight, so if I go from this weight to this weight, my loss will change from this to this. Okay. And our goal is to find this particular set of weights, which is optimal for this neural network. So what decides the loss? There are two things that will decide the loss. Okay, the loss surface. The loss surface is decided by two things. One is structure of the network. Okay, and second thing is training data. And weights are what you will change, along your x-axis. Okay, so I can only show you one weight here, but actually there is not just one weight. There could be millions of weights. So it could be a surface in millions of dimensions. But keep this in mind that if you change either the structure of the network or the training data, this curve will look very different. Okay. So now coming back here, so the way these weights are initialized, they are initialized randomly, right? So what that means is that you just initialize the weight here, some random weights, and now you want to do gradient descent. Okay, and with gradient descent, you want to be able to find good weights, and it's possible you'll get stuck here because this is your local minima. Okay. Uh, so usually your weights will be initialized randomly, and because they're initialized randomly, there can be issues with that. First of all, the weight should never be completely zero. That's never a good choice, because if the weights are completely zero, you remember your Jacobians when you are doing the gradient descent. Your Jacobian for one of the previous layers is dependent on weights from the layer that is closer to the output. So if your weights are zero, your gradients are going to be zero, and there will be no change in the output. Okay, there will be no change. There'll be no change in these weights. The training will become very, very slow. So some value like initializing all the weights to zero is never a good choice. The other problem with initializing everything to zero is that it will seem as if all neurons are acting as one. So if all these weights going into this neuron are the same as the weights going into this neuron are the same as weights going into this neuron, etc. That means all these neurons are the same, and they will collapse into one, mathematically speaking or computationally speaking. So there will be no way to train their weights differently from each other. Their weights will co-adapt. So never use the same value. Give some random value to the weights. Every weight should be randomly selected. Okay. So once you have random selection of weights, then they can still be a problem. Okay. Let me skip the math. Let me talk about random initialization. So random initialization will break the symmetry because you are randomly initializing the weights. It's the neurons will not behave as one. So some will uh, optimize in a different direction, others will optimize in a different direction, which is good because you want each neuron to extract different set of features. There is no use of each neuron extracting the same feature. Okay. So usually you basically sample it from Gaussian distribution. But then that is fine for small networks. For deeper networks, we run into problems with that. Okay. Uh, so let's say your weights are quite small, right? It's better if I show you the Jacobians, and then it will be easier to see. Let me see if I can show you the Jacobians. Yeah. Okay. So let's quickly revise backpropagation. So as you know, backpropagation is gradient descent. What you have in backpropagation is you have the final layer, and so actually there is another layer after the output layer. Can you guess what that layer is? So it's usually not shown as a layer. That's the loss layer. If someone said that in the chat, that I'll be very happy that you are getting the concept very well. Yes, that is the loss layer. There's a question from Abhilash. When will neural network converge if all weights and biases are initialized to zero? No, it will not converge. So that's exactly what we talked about. All right. So how is loss a layer? So let me show you draw a picture to show that. So let's say we have a neural network, right? So you have some neurons here. Okay. And these are your input neurons because your X has 4 dimensions: X1, X2, X3, and X4. Okay. Then you have some number of hidden neurons. Then you have some number of layers. And then you have final layer of hidden neurons. Okay. Then you have, let's say, some output. Okay. After the output, so these are your, let's say this is your probability mass function for three classes, right? So you have y1, y2, and y3, right? So you have y1, y2, and y3, right? So now what you do is you have a target variable, and that target variable is t1, t2, and t3 target vector, and this is one hot bit encoded. So let's say it is like 100, or it is 010, right? Or it is 001. And then between these two, you are fitting a cross entropy loss. Okay. So you can think of it as there's a cross entropy function here. My drawings are really terrible with my hand, but let me see if I can draw it cleanly. So let's say you have a cross entropy, you have another layer, which is a cross entropy layer, CE. And to that you give these inputs, and you also give these three inputs. Okay, these six inputs you give, and out comes the cross entropy loss. Okay. So this loss is actually, you're trying to reduce this loss. So you're trying to find the minimum of this loss. And that is what is being back propagated all the way here until this set of weights. Okay. All the other weights as well as this set of weights. So now when this loss is back propagating, uh, for for this particular weights, uh, there will be an entire chain of partial derivatives that will get multiplied at each layer. Okay. And what is in that set of partial derivatives? It's exactly the weights of the previous layer. Okay. And the derivative of the activation function at the point where it is activated. Is that clear to everyone from backpropagation lecture? Some yeses, some nos. No one is saying anything. Okay. Okay. At least some of you got it. Okay. So your derivative that will come all the way back here will have multiplication of this weight, this weight, this weight, right? So W2, W3, W4 matrices, all these matrices will be multiplied together along with the along with the point derivative of the activation functions at the points where they are activated. Okay. So if it is a ReLU, then it will be 1 for positive activation and 0 for negative activation. If it is sigmoid, then whatever it is on the sigmoid curve and so forth. So because you're multiplying all these weights together, if these weights are very small, then the derivative that will reach here will be very small. If these weights, all that are getting multiplied, W2, W3, W4, if they are very large, then the derivative coming back to W1 will be very large. So what will happen to the weights that you update when you update W1 weights? They will either take a very large jump or they will take a very small jump. Okay. So because of that, your gradients are said to be either exploding gradients or vanishing gradients. If you have exploding gradients, then your weights will become nan very quickly. They will become very large numbers very quickly. If they are vanishing gradients, then your weights will not move at all. They will not change at all. And that it usually afflicts the lower layers of the neural network because the loss is towards the upper layers. It's closer to the upper layers. Let's look at some questions. Okay. Does anyone has any questions on this concept? Exploding gradients or vanishing gradients? Show of hands if you have any questions. Let's see what's going on YouTube. Looks like no questions on YouTube. But it is an important concept. So if you have questions, please ask, because the rest of the lecture will build upon this concept. Okay. All right. So your weights here at the lower portion of the neural network will either get vanishing gradients or exploding gradients unless we do something about it. Okay. So let's see what can be done about it. Okay. So random initialization is not enough for deep neural networks because that can lead to vanishing or exploding gradients. Uh, so what has been shown in one of the papers that first analyzed this condition quite a bit. Basically, what they did was they plotted epochs or training iterations on the x-axis, and they looked at the activation value of neurons in different layers. So you have layer one, which is closest to the input. You have layer two, layer three, layer four, and layer five. Layer five is closest to the output, and they're looking at the activation value, which means what is the output, and this is a sigmoid layer. Sorry, tan h layer. So the tan h layer maximum value can be 1, minimum value can be -1. So what you see is that for layer 1, very quickly after a few training epochs, the value becomes either -1 or it becomes +1. For layer 2, after some time, the value becomes either +1, -1 or +1. Only for layer 5, it remains like between 0, -1 and +1, even after a lot of epochs. So what does this tell us? Basically, what it is telling us is that they are showing two different things here. They are showing both the activation and the gradient. Okay. Uh, so what this tells us is that there is some problem with the lower layers. They get saturated very quickly. When they get saturated, so if you go back to this tan h function or the sigmoid function, right? So this is the tan h function. So if all your activations are in +1 or -1, that means the gradient, which is the blue curve, is going to be 0, and the weights are not going to change at all. So that is a problem. So we try to solve that problem by choosing a different activation function. We already talked about ReLU. So in ReLU, basically, at least for the positive half, at least for let's say half the training samples, there will be some gradient. For others, there will not be any gradient. There is a slightly better version of ReLU. It's called leaky ReLU. So in the negative half also, it has a slope, so it never gets saturated. But this still does not fully solve the problem. Uh, There are four curves for layer one. Does it mean that input layer has two nodes, four weights? Or I think it has four different neurons, maybe. I'm not sure. I forgot what's in the paper, but the point was that it gets saturated very quickly. Uh, so even choosing the activation function does not fully solve the problem. Okay. So the solution is to better initialize the weights. How do we initialize the weights? We initialize the weights so that the expected output, the variance of the output that you get from each layer, it should not be too spread out and the gradient should not be too misbehaved. Okay. So this is what the activation value, the distribution of activation value is for the first layer, which is the red curve, second layer, which is the black curve, third layer, which is the blue curve, etc. And then you have the final layer, which is the layer 5. So what you can see is that for layer 1, okay, it's quite spread out. So the distributions are not the same. They are not. They're very different from each other. Okay, and because there's a lot of variance in layer 1, because of that, it saturates very quickly. Same with the gradients. The gradients are much more, the gradients are closer to 0 for layer 1, and they are much more spread out for the other ones. But if we initialize the weights better, then we can actually have uh, the distribution of the activations as well as the gradients quite equal to each other among the layers, so that they all of them train together. It's not like the only the top layers are training and the lower layers are not training. So how do we do that? So the idea is that you look at the variance of a particular layer. Okay. And you look at, so for forward propagation, if you look at the variance of one layer, it should be the same as the variance for another layer. So what is this z? Z is basically, first you compute the linear output, which is for the previous layer, the output of the previous layer times the weights plus bias, and then you put it into the activation function, which is the tan h function for this particular example, and this is how you get zi plus 1. Now the variance of any two layers I and j, the activation variance of the activation should be the same, number one. Number two, the variance of their derivatives should also be the same. So del a by del L by del A is that linear output. It should be same for both activations. So if we solve for these two conditions, what we get is that number of neurons in any particular layer times the variance of the weight should be 1. Okay. And the number of neurons in the next layer times the variance of weight should also be 1. So roughly what we get for tan h is that your weight should be initialized from a uniform distribution, which is between root 6 by nj plus nj plus 1. So j is the layer number, to minus of that to the plus of that. Okay. So if you do the Xavier initialization, for deep neural networks, your lower layers will not be stuck. Okay. Let's look at some questions now. If neural network is very deep, will it help? Yes, the better initialization of weights will help. What is on the y-axis of the graph? Y-axis is the probability or the frequency of activation, or the frequency of the value of the gradient. Okay, it was a frequency distribution histogram. So so this is the formula for Xavier initialization. Yes, Hardik. Okay. Uh, so basically, if you take any package like PyTorch or TensorFlow, chances are that Xavier initialization is now a standard call within those packages, and you don't even have to worry about it while while doing the initialization. This works for only these fully connected neural networks that we have talked about till now. This is not the formula for convolutional neural networks. So that analysis is slightly more complex, but it's also something that you will find in the packages, Xavier initialization. So Xavier initialization worked well for TANH. So then came something called He initialization. And this one was an analysis for the ReLU activation function. And based on that, he also suggested on similar lines what formula will work best for ReLU activation, so that the gradients don't die out towards the bottom layers that are closer to the input. So you can look this up, or you can use it as a direct call in the neural networks. Okay. So that was all about weight initialization. Now I will move on to the next topic. Any questions on weight initialization?
So, sir, Xavier is for only 10H and he is for only Rail 1.
Yeah, so people have extended these two other activations. So a lot of these are now standard library calls within TensorFlow and Keras and PyTorch. Okay. Yash?
Yeah, sir. So we would not have to do these kind of initializations ourselves.
No.
Thank you.
Only if we give you a statistic assignment that do everything from scratch, then you have to do this, which we will, so that you understand
This
how
one,
things work.
this initialization, sir.
I'm not sure what the upcoming tutorial assignment has. But it's pretty straightforward, right? Like Xavier initialization is so easy. You look at the uniform distribution, right? Uniform distribution is built into like all math libraries like NumPy.
Yeah. Yes.
Yeah. Yeah. So Xavier used fan in and fan out. Yes, that's correct, Hardik. Ashish?
Sir, our goal is that the weight should not, like when back propagation is coming through, or even if forward propagation is happening, our goal here is to see that first of all, the distributions of the layers should be similar.
Yes.
Second, they should also not saturate, right? They should
Yes. The
they should
active,
have a bigger variance in
right.
or
They should not have too big of a variance either, because anything that has a big variance, that any neuron that is on the tail end of a big variance will saturate.
but in that case, even if the variance is big, still things will be centered around. So it can kind of says that weights are getting initialized like in a nice balanced manner rather than just being centric
Right.
to between a certain interval, right?
Right. It should not be too narrow. It should not be too broad.
Okay, so it should be a balance. Okay. Thank you,
Right.
sir.
Okay. So now let's look at how we can improve gradient descent. So quick revision that let's say, sorry, my blue dots are shifted. Uh, so these blue dots were supposed to be at the Mhm. At the bottom. So this is where it should be. It's important from PowerPoint, and then this thing shifts it a bit. Okay, that's fine. Uh, so let's say you are trying to maximize or minimize a function. So if you want to, so this was one of the quiz questions, right? So if you are trying to minimize a function, let's say this is your fx. So this is a convex function, and your f dash x will be a positive value, and then f double dash x for this parabola ax square plus bx plus c would be a positive value. On the other hand, if you have a concave function, then your double dash would be the second derivative of the function will be a negative value. Okay, so what is the second derivative? It is 2a. So if a is positive, then the parabola opens upwards. If a is negative, the parabola opens downwards. So everyone knows that. So we will use this to our advantage to design better ways to uh, do gradient descent. So in 2 dimensions, the story starts to become a little more complicated. You have x1 dimension and x2 dimension. Actually, in neural networks, it will not be the inputs x1 and x2. It will be actually weights w1 and w2. So let's say this is w1 and w2 dimension, and you want to go to the bottom of the loss with respect to w curves. So for any given point, you can define the gradient with respect to the two inputs, right? So these will be, let's say, two weights, and you will get two numbers which can be arranged into vector. So that is your gradient vector. And what does it do? So so let's say in the w1 w2 space, you have contours of equal loss, and you are on a particular w1 w2 value, uh, which is this particular point. Your gradient will be an arrow which will be perpendicular to the tangent here. Basically, it is telling you the direction of the steepest ascent. Okay, so this is example of a gradient of a simple function, and we'll be taking small steps to get to the bottom of the bowl. All right. And the way we do that in neural networks is that first we have to compute gradient with respect to all the weights. And for that, we use chain rule of differentiation on computational graphs. So this is also something you have looked at. So let's say you have input X times weight W1, you get some quantity, you add the bias, you get Z1, you send it through ReLU, you get A1, you multiply that with W2, you get something, you add b2 with that, you get z2, you send it through softmax, you get a2, and then you compare it with the target and compute cross entropy, and you get the loss. Now you want to compute the derivative of this loss with respect to this weight w1 or this bias b1 and w2 and b2, right? So you back propagate this loss. So you take its partial derivative with respect to a2 with respect to a2, the partial derivative of a2 with respect to z2, which is the derivative of the activation function at that point, at the point z2. Okay. So all these partial derivatives are getting multiplied. Then derivative of z2 with respect to whatever this quantity is, derivative of this quantity with respect to a1. So I'm trying to get to w1. If I don't want to get to W1, then I don't need to worry about A1. I just directly compute the derivative of this quantity with respect to W2 and I'm done. But I also need to compute with respect to W1. So I compute the derivative of this quantity with respect to A1, derivative of A1 with respect to Z1, derivative of Z1 with respect to this quantity, and derivative of this quantity with respect to W1. So that's how, using chain rule and using a computational graph, I will be able to adjust W1 because now I know the gradient of the loss with respect to W1. Except W1 is not a single weight. W1 is a vector of weights. Okay. W2 is also a vector of weights or a matrix of weights. Okay. I can arrange that matrix into a column wise into a single vector. So because now your output can have multiple values and your weights are also vectors. So basically we get a Jacobian. Right? So those Jacobians get multiplied as you go back. Okay. So point of all this is that now let's say if you want to do gradient descent with respect to W1, one single element of W1. Okay. So how do we do that? So let's say this is your loss curve. This blue curve is your loss curve. Okay. And you are at this particular point in the W1 space. Okay. So here, how big of a step should I take so that I reach the bottom of this curve? So this was one of the questions in the quiz, that this particular parabola, let's say even if it was a completely ideal parabola, and another parabola can pass through the exactly the same point with exactly the same tangent. There are infinitely many parabolas that can pass through the same point. Okay. So even if you knew that it is a perfect parabola, you don't know which parabola it is just by knowing the loss and just by knowing the gradient of the loss. Okay. To know which exact parabola you are on, you need to know the second derivative of the parabola at that point, not just the first derivative. Okay. Is that clear? So the second derivative in multiple dimensions is called a Hessian matrix. And the whole problem with optimizing neural networks is the problem with how the Hessian matrix behaves. And there are different ways to uh, basically make use of an approximation of the Hessian matrix to get to the bottom of the uh, local minima faster. Okay. And it's also possible that your function is not convex at all. It could be that your function is something like this, where you are actually close to a local minima and you will never find the global minima. And let's go back to the neural network. Do you think it is a, so let's look at this neural network. Do you think this is a convex function with respect to loss? Is cross entropy a convex function? I guess everyone knows it's a convex function. Is softmax a convex function? Softmax is actually not a convex function. Is ReLU a convex function? It is a convex function. Okay. Uh, so if you have a function of a function and both functions are convex, then the final function of that f and g, right? So if you have function f and function g, and f takes the g as a function, then if both are convex, then f of g is also convex. But first of all, we don't have a convex function here. Secondly, we also have weights somewhere inside. We have W1, we have W2, etc. Right? If the weights are not positive, then there is no guarantee that the resultant function will be convex. The weights have to be, if you add two convex functions, then or if you take a function of a function multiplied by something, and that multiplication factor need not be positive, then there is no guarantee that it is convex. So actually, your loss surfaces for neural networks will not be convex. You will only be getting local minimas. Now, is that a problem? Should we be worried about, should we be obsessed about finding the global minimum? I will answer that in a bit. But first, let's see how to even find the local minimum in a fast manner. Okay. So let's say if we just know the gradient, right? And this is your loss function. If I take small step, I will not reach the bottom. If I take a perfect step, then I will reach the bottom. If I take too large of a step, then I may land up here. If it is even larger, then I actually may end up increasing the loss, and the loss will quickly become will diverge. So how do I know the learning rate? How do I find the learning rate? Okay. So how do I adaptively, algorithmically change my learning rate? That is what we'll talk about. So the perfect step size is going to be based on the knowledge of what is the second derivative. Okay. Assuming that the loss is locally parabolic, at least in that neighborhood. So if we knew that, we would know exactly how to reach the bottom in one step. Okay. But many times we don't know that. And to estimate the second derivative and actually we have to take the inverse of the second derivative. That is quite expensive in large dimensions. I will tell you how. Okay. So first of all, there is no such thing as a single second derivative in multiple dimensions. So let's say you have weights W1, W2, W3, Wn. Okay, and f is your loss function. So your second derivative is not just del square f by del W1 square. Okay, it's actually a matrix. It's a n by n matrix where n is the number of weights. So you have del square f by del W1 square. Okay, the diagonal elements will be del square f by del xi square or wi square. But then the off diagonal elements would be one time you will take a derivative with one weight, then you will take the derivative with another weight. So it becomes a matrix. So if you have 1 million weights, your matrix size is 1 million squared. Okay, or 1 trillion. 1 trillion entries in this matrix. Of course, it is a symmetric matrix, so roughly 1 trillion by half, 1 trillion by 2. Okay, but still of the order of million squared or weight squared. And now what we want to do is, if we want to take a perfect step size, we have to take the inverse of the second derivative, which is the inverse of the Hessian matrix, and multiply. So we'll get again an n by n matrix, and we'll multiply it with the vector, which is the n dimensional vector, to get an n dimensional step update to get to the bottom of the curve. Now inverting a n by n matrix takes n cubed operation. So trillion times million operations. If you're smart about it, it can take million to the power 2.7 using some smart algorithms. Yet, suffice it to say, we don't want to do it for large neural networks. So what do? We need to find out some approximations to invert the Hessian matrix or some other tricks, and to basically find out what is the curvature of the loss surface in different directions at the point where we are at the weights, at our current weights. Is that clear? Any questions? Okay. All right. So how do we do that? Uh, so before that, I want to talk about what are some other problems that you will encounter with because of this multi-dimensional optimization. So in single dimension, your function was either locally convex or it was locally concave. Look at these directions. There is this direction in which the function has a minimum, but then there is another direction at the same point where the function is a maximum. So what that means is that you can actually have functions that are locally, they have minima in one direction and maxima in another direction. So such points are called saddle points. At this particular point, the locally, if you sit and look at, you will find a flat surface where the gradient is 0. But the second derivative in one direction is positive. The second derivative in another direction is negative. Okay. So now these directions need not be actually parallel to the axes. These directions need not be parallel to W1 and W2, but actually some combination of W1 and W2. One direction could be W1 minus W2. The other direction could be W1 plus W2, for example. Okay. So the way we think about it is that you go back to this Hessian matrix, right? So at any particular weights, set of weights, W1 to Wn, the eigenvalues of these Hessian matrix, if they are all positive, then you have reached the local minima. If even one eigenvalue is negative, then you might be at a saddle point. Okay, and you would not know that because you are not going to compute the Hessian. It's a very non-trivial task to compute the Hessian. So if you have a million weights and you reach a point of zero gradient, chances are you have not reached the bottom, you have not reached the local minima, you have actually reached a local saddle point. That you, there are some unexplored directions at that point where you could go to further reduce your loss. Ritvik, what's your question? Ritvik? All right. Clear? So your complicated loss functions will actually look like this. You might be here, you might suddenly go down, you might reach a flat region here, but it is actually a saddle point because you could actually go somewhere else and reduce it further. And you might end up here in a local minima. And you may or may not escape from here. If you escape from here, you might reach the global minimum. Okay, so you never know where you are. Okay, so one trick that is used to get out of local minimas and to find the bottom or roughly the bottom of the surface, lost surface, is to do something called learning rate scheduling. Okay, so let's look at three different learning rates. What is learning rate? Learning rate is that eta that you multiply to the gradient when you update the weights. Right, so where is your gradient descent? Maybe I don't have it here, but remember your next iteration weight wt plus 1 is wt minus eta times gradient of loss with respect to wt, right? So that eta is your learning rate, so that is your step size. Now if you look at these three curves, one curve is a green curve, the other is a red curve, the third is a black curve. The difference between them is that all three of them have very different learning rates. The green curve suddenly reduces as the training iterations go. Okay, it goes down faster for because it's a large learning rate, and then it doesn't actually go much further down. It might actually saturate here or it might go up. On the other hand, the red one, which is an intermediate learning rate, will slowly go down, but then it will converge to a larger loss than the third one, which is a painfully slow curve for a small learning rate, but it goes much further down. So can I have the advantage of the three together? The way to do that is to change your learning rate as your iterations go. Start with a high learning rate. When your loss starts to saturate, reduce your learning rate. Then when your loss saturates again, reduce your learning rate further. Okay, so there are different ways to do that. You can do linear reduction in learning rate, exponential, square root, or stepwise or cosine change in learning rate. So I encourage you to look at learning rate scheduling as it's its own topic in optimization, and it's used quite a bit in neural networks. Okay, so question is why we don't get stuck in local minimas, and even when we get stuck in local minimas, why do neural networks still have very good performance? So the reason for that is that when your neural networks are very large, right, when they have a lot of parameters and a lot of layers, then it has been shown approximately at least that your local minimas are close to global minimas in terms of error. Okay, and if you reach a point of zero gradient, you are much more likely to be on a saddle point than actually to be on a local minima. And then there are all these techniques like SGD that help you escape these saddle points. So let me quickly show you why we shouldn't be worried about global minimas. Okay. Uh, so here's an experiment for some, not the actual neural networks that people use all the time, but it is basically on some simplified neural networks. Some people have conducted some experiments. What they have shown is that if you get stuck in a critical point, what is critical point? Where your gradient is zero, and you look at the index of the critical point. What is the index of the critical point? How many eigenvalues of the Hessian, how many directions, okay, are actually leading to a reduction in loss. Okay, how many of them have a negative eigenvalue? What percent of eigenvalues are negative? So let's say if we have 25% of the eigenvalues are negative, then your training error is high. But as soon as you reach a point where you don't need to have zero critical point, index of the critical point need not be zero. You may still have some directions to go where you can reduce the loss, but you are not that far away from the optimal. They have shown it on multiple data sets. So finding the absolute minimum is not that critical in neural networks. Basically, that's what they were trying to show. Okay. And the other problem with finding the absolute minimum is, I will go back to this example. Here, if you look at this, what determines this loss curve? What determines is the structure of the neural network and the training data. So this absolute global minimum that you see is minimum only for the training data. It need not even be minimum, absolute minimum for the test data. For your test data, it's possible that your curve will actually look like something like this. Okay, where this whole band is good loss, right? It gives you good performance, but it doesn't matter whether you are here or here, whether your weights are here or here. So even if you get stuck in a local minima in training, it chances are that you are very close to the global minima, or it will very close to getting good loss performance. So you don't need to worry about, obsess about finding the global minima. Is that clear? Okay. So let's go back to this, how we can use this to our advantage. So which means that we will only be talking about reaching the local minima fast and escaping the saddle points. Okay. So these saddle points, like I mentioned, they are characterized by Hessian eigenvalue of a Hessian matrix that is negative. At least one of them has to be negative. So JD has brought up a very good point. When you are doing mini batch based training, then with each mini batch is its own training data. Your loss is going to change. In fact, that's what we use to escape saddle points and local minimas. Okay. So for a very, if you have a plateau, then your second derivative is zero, your first derivative is also zero for all directions. If you have a local minima, then your first derivative is zero, but your second derivative is positive. Okay, your eigenvalues of the Hessian matrix are positive. For saddle points, some eigenvalues are positive, some are negative. For long furrows, some are zero along this direction, others are positive. So these are all things that are problematic for gradient descent. Okay, I'll skip this. So I already mentioned that we don't use second order methods because they require lot many more operations. So how do we escape these local minimas? We basically randomize the data. So we add some noise to the training process, and we can do that in multiple ways. One is that we can add noise to the data itself, in the sense that we can randomly have mini batches, or we can do SGT, right? So each time, with each batch, you are actually descending on a different surface. Second is, you can actually perturb the gradient itself by adding some noise to the update. And that is what momentum does in some sense. Okay. Or you can add some noise to the input itself, random noise to the input itself, which is called data augmentation. That is quite a popular technique these days. All right. So now let's look at gradient descent and gradient descent with momentum. Okay. So let's say you are doing gradient descent. Your weight update at t+1 would be the previous weight minus eta times gradient for all samples, okay, at that particular weight. Okay. Now, so that gives you only one direction, and that will be your update. If you are doing SGD, then you will be taking a random subset and you will be computing the weight update. So you can actually go in any direction. Okay, so GD requires, gradient descent requires more computation per update. SGD is more noisy, and but it escapes these global minimas better. Sorry, local minimas better. So what SGD is doing, so let's say this dotted curve is the loss on the all the training data, but your purple curve and the brown curve and the blue curve are loss surfaces for different mini batches. So what might be local minima for the purple curve, as soon as you go to the next iteration and you change your sample data, you might be on the blue curve and it may not no longer be a local minima and you may still have a direction to go. So now because their minimas don't align towards the bottom of all their surfaces, you will have some noisy updates, but otherwise you are doing fine. Okay. All right. Any questions on YouTube? Doesn't seem to be. Okay. So another way to introduce noise is to use something called momentum. Okay. So what you understand by the term momentum in physics is that a body in motion tends to stay in motion. A body that is has stopped tends to be difficult to get started, right? So roughly the same concept is being used here. So let's say your vanilla gradient descent is that your weight update is previous weight minus eta times the gradient of the previous weight. Instead of that, what we will do is that we will not only add this particular gradient times the eta, but we will also keep a certain portion of the previous weight update. Okay, we'll keep a certain portion of the momentum. So let's say if you were to just compute the gradient of the weights at this step, that would point in this direction, or the negative of the gradient in this direction, minus eta times gradient would point in this direction. Instead, and the previous weight was like somewhere along this direction, right? So we will keep going in that direction and we will take the new direction and their vector sum and we will end up here. So we will scale the negative of the gradient by eta. We will scale the previous update from some point here, we jumped here. We will scale that by a factor alpha, and the vector sum of that is where we will end up as our weight, new weight. So what this does is, let's look at this example. This figure has become messy. Let me draw it again. Okay. So let's say you have a curve like this, right? And you had some weight update that ended up here. Okay. So here now there is a small step if you just look at the gradient, because here the slope is very small. So instead you would just be stuck here. But because you are taking eta times this step and alpha times the previous step, you might end up having a slightly larger step and you might go over the hill and into the next one and over the hill into the next one. On the other hand, if you have a large step, okay, so how does it work? Basically, yeah, if you have a large step and now your gradient is pointing backwards, but you had the previous step that was this way, depending on which one is stronger, you might actually slow down instead of going further up. You might actually slow down and converge to the bottom. Okay, so setting this alpha value and eta value is critical. You need to play around with it. Let's look at some questions. Okay, how do we obtain the scaling factor alpha? Okay, so it's a hyperparameter. There's a good recommended value which is 0.9. It cannot be above 1. If it is above 1, then you can see that this is a geometric series of weight updates. If you look at the absolute value or the L2 norm of the weight update, so it will keep adding and it will actually diverge. So it cannot be above 1. It cannot be below 0 because that doesn't make sense. 0 also doesn't make sense. Then you are back to the gradient descent equation. So it is somewhere between 0 and 1. Good value is 0.9, 0.8. You can try those. Okay. An advanced form of momentum is that instead of taking the previous weight update and the gradient, you first compute where you would land up and you scale that instead of the previous step update. So that's called Nesterov momentum. Okay. So it's a better correction for bad velocity. So this alpha, or here it is called rho, it is called a damping factor. Okay. So here's a good visualization of how you are trying to get to the surface. So notice how bad the contours are. Look at the blue curves here. Okay, I will play this again. Forget about the orange lines for a minute. Just look at the blue curves. So look at how bad the curves are, that your minimum is here and your curves are oriented in like very thin long way, and like you're starting here because that's your random initialization in this W1 and W2 space. Now, if you, so each of these blue, orange dots is the next step update based on your step size and momentum. So momentum can be between 0 and 0.99 or 0 and 1. And your step update, the eta here, they're calling it alpha. Eta can be anything, right? So here, what you can see is that as you increase the momentum, there is a faster hurry to reach the optimal, but then you overshoot the optimal. Look at how when it is increased, there are fewer steps, but then you oscillate around the optimal. This is the good value. Now it has become worse than the good value as you go to 0.99, a lot more oscillations. Okay, so around zero point 0.9 is a good value that you reach your optimal very fast. Okay, so this is momentum. There are some more advanced optimizers, such as AdaGrad, RMS prop, Ada delta. Their basic idea is the following, right? The basic idea is that if you are in a flat region, right, if you have reached a region where you are in a plateau and you are not finding good directions, better to start to take slightly larger steps. It's a little bit counterintuitive. Gradient descent, your steps become smaller in those regions, but here you are saying that if you are, if you look at all the gradients, right, for all the previous steps, and all your previous steps have been small, right? You look at the you look at it weight wise, you are looking at only one weight at a time, but you are looking at all the previous steps. So a series of previous steps have been small, then that means you are in a long furrow for that weight. Let me show you what a furrow is. Let's go back. Yeah, so look at this furrow. This is a furrow, right? So in this direction, for this particular weight, you need to take larger steps. For the other particular weight on the other direction, you may not need to want to take very large steps. You want to escape the saddle point for this direction. So here, if your weight updates in this direction have been small, then might as well speed up in that direction. Okay. So how it does that? It basically keeps a running sum of all the previous weight updates, and it divides the gradient by that. Okay. So here, this particular thing in the denominator is always positive, so that the sign of the gradient does not change, and it is still eta times the gradient, minus eta times the gradient. Okay. So it automatically reduces the learning rate with t, and it also automatically speeds up when you reach smaller portions. Okay, so and then there are slight variations of this particular concept in AdaGrad, RMS prop, and Ada delta. The optimizer of choice these days is Adam, which incorporates both this scaling idea, scaling of the gradient, as well as the momentum idea together into a single optimizer. So it basically combines AdaGrad and momentum. So what it does is, look, first let's go down. Your weight update is your current weight is previous weight minus something which used to be minus eta times gradient of the weight. Okay, so that's what it used to be. Instead of that, what it does, it takes this concept from AdaGrad, where it looks at the gradient and divided by the sum of the square root of the sum of the squares of the gradients for the last several steps. So what it does is, instead of that, it replaces it with the first moment and divided by the square root of the second moment. And how does it compute the first moment and second moment? So your first moment is basically exponential running average of the first moment, starting from by incorporating the gradient in it. And the second moment is the exponential running average by incorporating the gradient squared in it for this particular weight. So it doesn't look at interaction between different weights. So the off diagonal terms of the Hessian, it ignores that. It only looks at the diagonal terms of the Hessian in some sense. Okay. So it simplifies the problem. Both momentum, adagrad, RMS prop, Adam, they all simplify the problem by just looking at the diagonal of the Hessian, not the off diagonal terms. Okay. So what is this exponential running average? It is controlled by these parameters, hyperparameters beta 1 and beta 2, and these are again between 0 and 1. Okay. And then there is some bias correction, so you divide it by 1 minus beta 1 and 1 minus beta 2 to the power t, number of iterations. So there are some recommended values for these beta 1. I forget what those are. I think one is 0.9, the other is 0.999. Just look at the you will find it very easily. There are standard values that are it is even initialized to standard values in Keras and TensorFlow and PyTorch. So those are good places to start. Okay, let's look at some chat questions. Yeah, think of the momentum as if you leave the ball from a starting point, how quickly it will reach the optimal and how it will settle down. Yeah, okay, sounds good. All right. So now let's look at a visual of what happens when you compare all these optimizers together. Okay. So this is your optimal point. Okay. You have SGD in red, you have momentum in green, you have Nestrov accelerated gradient in purple, Adagrad, etc., and RMS prop. Adam is missing here. But you can see in this, and then you have a saddle point, and you want to see how quickly. So you will oscillate because you in this direction because you think you have found the minimum, but you want to escape in the other direction because that's where you have the maximum, local maximum. So you can see which one escapes faster, right? So you can compare these two visuals. So in general, SGD takes a long time to converge, long time to escape saddle points. Okay, these other more advanced optimizers, they do a better job. And in general, Adam is a good choice. It probably does even better than the ones that are shown here. For most cases, you can always have a pathological case where Adam actually doesn't do as good as some of the other ones. Okay. Any questions on making gradient descent faster? No? Everyone understood everything? Yes, Ashish.
Sir, a stochastic gradient descent means it's generally related with the batch size, right? So if I keep the batch size as 1 and I choose one of these optimizers, then it is optimizers and these things are different, right? I mean, this is based on stochastic gradient
Yeah,
descent is actually based on the batch size. The other things are
yeah.
different, yeah.
So that's a good point. You can actually, it's usually customary to combine the two. So
Oh
when we
yeah.
say
So
stochastic
basically,
gradient descent, it is without using any of these other things.
so that means vanilla gradient descent.
Vanilla
Yeah.
gradient descent,
Yeah.
yes.
Okay. Thank you, sir.
So here, usually you combine stochastic gradient descent with RMS prop or with Adam. So you still do mini batches. And there's a good computational reason to do mini batches because you usually choose a mini batch as large as whatever you can fit in your GPU memory. Questions in chat. Yeah. So when we say SGD, it's a sample update only, strictly. Questions in YouTube. Let's see. There is a question. Uh, Pratt Sukha is asking, even using the Hessian matrix, can we get the global minima for certain? No, we cannot get global minima for certain, even when we use the Hessian matrix, because this is not guaranteed to be a convex function. The loss is not guaranteed to be a convex function. Then Shikhar is asking, can you explain Nestrov one more time? So let's go back to Nestrov. So in vanilla, sorry, in classical momentum, basically you had some update, right? You had some previous weight update, WT minus 1. So let's say that was this particular, the where I'm moving my cursor. So you take an alpha times of that, so you continue to go in that direction due to momentum, and then you have a new weight update, and you take the vector sum of that, and that is your actual updated value now, right? Instead, in Nestro, what you do is you are looking at the previous weight update, and and where the momentum would have taken it. Okay, so you are looking at the weight and where the momentum would have taken it, and based on that you are basically doing a correction for the velocity update that you would get. So you don't compute the gradient on the previous weight alone, you compute it on uh, previous weight plus alpha times the momentum Vt. So this Vt is the difference of two weights, and Wt is the previous weight itself, right? So you basically do that correction in that direction. So you can see that if there is a discordance in the two directions, this was going here, this was going here, then instead of like taking the vector sum, you first go here, compute the gradient now here, and then that is your weight update. Okay, so it does a little bit of braking in some sense. The brakes have been applied in the direction where it would have gone. Okay, if there's a difference in the directions. All right. So we already covered this. Kasina, what's your question?
Hello.
Yeah,
Sir, in the visualizer you showed,
yeah,
we are not computing the Hessian, right? Anywhere
no,
in the organ. So, could you please go to the visualizer?
yeah,
Yeah, I have it here. ADA delta seems to not at all oscillate and directly go. But
yeah.
how is that possible? Only if we compute the Hessian, then we know if it is a saddle point or it is a plane point, right?
Yeah, yeah.
Then
So
how
here it's actually they haven't taken a pathological case where the escape direction is actually a combination of two weights. Here it is a simpler case where you just have to make a better update in one weight's direction. So this cartoon figure may change in a real situation. So don't go by just this cartoon that ADA delta is doing very good.
yes.
Okay. Okay. So we already talked about why finding the local minimas is good enough. Your bigger problem is to escape saddle points, not to obsess about global minima. Okay. So now let's look at some other ways of including some sort of randomization or including some sort of a normalization to help the neural networks train better. So one way to introduce randomization in a neural network and break the symmetries or the co-learning of different neurons is something called dropout. So it's almost like it's actually can be thought of as a regularization technique also. Divya, you have a question?
Sorry, I raised my mistake.
Okay. So it's a regularization technique. Basically, what you do is, let's say you have a neural network. Okay, so these are your input nodes. These are your first hidden layer. This is your second hidden layer. This is your output layer. So it's fully connected. Every neuron here gets input from all the previous neurons. Every neuron here gets inputs from all the neurons in the previous layer. Now, what we will do at training time, we will train in such a way that randomly we'll decide that certain percent of neurons in the first layer don't exist. That means the neuron doesn't exist. That means the weights coming out of it, the connections coming out of it don't exist. Okay. So basically what you get in this neuron is this input times weight W1 plus 0 times second input plus zero times third input plus this weight times this input plus this weight times this input. Okay. So you pretend as if the two neurons that you dropped out in the first layer, they don't even exist. Okay. And you can do that by turning their weights to 0. Similarly here, so because it is not going to supply any input to the next layer, it need not even have inputs from the previous layer. Okay. So if this neuron is randomly dropped out, this is all random. Okay. So every training iteration, you're doing this randomly. So this is not going to supply an input here. It is not going to supply an input here, obviously, because this is also dropped out. It's not going to supply an input here, here, or here. Okay. So these neurons are dropped out. So how do you decide which neurons to drop out? First of all, it is random. So there is something which is called a probability of dropout. So let's say the probability of dropout is p is equal to 0.25 for the first layer, 0.15 for the second layer, zero point 0.1 for the third layer. That means at any given time, on an average, 25% of the neurons of the first layer randomly chosen will not exist. 15% of the neurons of the first hidden layer will not exist. Okay, 10% of the neurons of the second hidden layer will not exist, and so forth. Okay. Any questions on the method, and then I will explain why we do it. Let's look at the chat. Can we think of dropout as something like lasso? No, because lasso not only sets some weights to 0, it also reduces the magnitude of the other weights. Okay, it brings them all closer to the 0, closer to the origin. Okay, so it actually doesn't do that. And it's not random. Lasso is not random. This is random. This is stochastic. Okay. Then next question is, won't it be wrong result if the neurons are removed from the input layer? Result is a result, right? Result is how you code the output. So it will give, yeah, so it will not have, so let's say you have uh, temperature sensor 1, temperature sensor 2, pressure sensor 1, pressure sensor 2, and seismic sensor, right? So two sensors as if they went offline. You didn't even measure you couldn't measure their input. So yeah, it will do some wrong processing, but there is some advantage to it. Let's talk about it, what the advantage is. So the advantage is that for any neuron, let's look at this neuron, right? This neuron was dependent on this neuron, this neuron, this neuron, this neuron, and this neuron. It was dependent on 5 neurons. So now it is forcing this neuron to not be overly dependent on all the neurons in the previous layer. What does that do? So what that does is that if by chance, let's say two previous neurons were giving you correlated activations, so it will break that correlation. It will, if one of them is turned off, that its weight will not be updated while the other one will be updated. So it helps them break these symmetries. It helps them learn independent features because they are also extracting features from the input. And then it is trying to see whether if you drop out input neurons themselves, then it tells you that try to make a good decision even if some input dimensions are unreliable. Okay, some dimensions are unreliable, some features are unreliable. So it basically tries to make them learn from noisy data. So it is as if you're training several neural networks together. This is one neural network. Another neural network would be when some other neurons are dropped out. Okay, it will look like a different neural network. So all these neural networks, several different neural networks are being trained in different iterations. How many different neurons? 2 to the power n, where n is the number of neurons, because any of them can be dropped out at any given time. So you're training different neural networks and your output is almost like an average of different neurons. So that's an ensembling of some sort that is going on. And each neuron is learning something independent. So it has been practically shown that it gives you better training and test performance. It gives you, it prevents overfitting. Okay. And theoretically, it has shown that it is almost like a Bayesian averaging of different neural networks in an ensemble. But there are some caveats, right? You cannot drop out too much. You cannot drop out too little. If you drop out too much, then you don't have enough information to make any useful decision. If you drop out too little, then you're not doing enough to break the symmetries. And the dropout, what is a good dropout rate for layer 1 need not be the good dropout layer for layer 10. What the probability of dropout for layer 1 need not be the same as a good probability of dropout for layer 10. Okay, let's look at some questions. Yeah, so you are building some sort of fault tolerance in the neurons, right? If we dropped out a neuron, should we then we should have ignored it as a feature? Yes, they are. Yeah, so the answer is what JD is saying. You don't drop out the same neuron in every iteration. So the same, if I dropped out this neuron, it will come back in the next iteration most likely, and most likely this one will be dropped out. Uh, so basically, it is not the same neuron that is being dropped off all the time. What is the use of feature selection? Aryan, I didn't understand your question. Can you explain? Oh, feature selection. Okay, so why did we do feature selection before we put it in the neuron in the neural network? Uh, so feature selection does break some of these symmetries. So even like the internal neurons that you have here, right? The on which you don't have much control, they can become correlated in their activation. So there is no guarantee that even if you do feature selection, there will not be like some symmetries in the neural network that need to be broken. Any method on how to elect different dropout rates for different layers? Yeah, so basically the way to think about different dropout rates is that usually near the input you don't use a very large dropout because it is critical to use all the inputs, and then rate slightly increases towards the middle. There's some good guidelines that are available on how to what dropout rate to set for what kind of an architecture and what layer, what different level of the layer. So do look it up. It changes from situation to situation. What works for a CNN may not work for an LSTM and so forth. And yes, like JD said, the computations become cheaper when you use dropout. So there is a caveat that you don't need to worry about. The libraries already take care of it. And that is the following. Look at this particular neuron, right? Here, when there was no dropout, it was getting input from 5 different neurons. Now, because of dropout, it is getting input from only 3 neurons, right? So the average activation, magnitude of activation for this neuron has reduced now, okay, because it is not getting so many different inputs. The variance of the activation here has reduced compared to this neuron, right? How much has it reduced? It is reduced by the factor p. P is the probability of or 1 minus p, where p is the probability of dropout. So while training, you scale up the activation by 1 by 1 by 1 minus p, so that it acts similar to what it would have done without the dropout. Okay. Is it easier to evaluate compute asymmetric neural networks? Asymmetric, yeah. So you mean dropped out neural networks? Yes, it makes such computations cheaper. Can you compare computations between symmetric and asymmetric? So if you're talking about standard and dropout neural network, in dropout neural networks, you have fewer computations. How many fewer? Basically, at least a factor of p if you are dropping out p neurons. Perhaps, no, maybe more than that. Maybe uh, because you are also dropping out the weights. Yeah, you'll have to compute that, how much that is. Any questions in YouTube? Okay, not really. Okay, so I encourage you to use dropout in training neural networks. Another quite useful technique in training neural networks is to use something called batch normalization. So what is batch normalization? So basically what we say is in batch normalization is that if you look at a one particular activation of a neuron, right, chances are that it is quite saturated either saturated or it is quite small. So the gradients are either vanishing or uh, they are exploding. So what can we do about one particular neuron? So let's say you have a particular neuron, okay, and you are just looking at that neuron's activation. What if I take an entire batch of inputs, and that entire batch will activate that neuron in a different in for with different values? What if I take that range of values and then normalize them to, let's say, something like a zero mean and unit variance? Would that help me standardize the magnitude of the gradient that is flowing back from this neuron? So what I will do is I will compute the mean of the activation for a neuron for that particular mini batch, and I will compute the variance of that activations for that mini batch, and I will normalize it, and I will the train the neural network based on that normalized value, and I will compensate for the normalization that I did later on, so that there is no sudden weight change, there is no very little weight change, the weight changes are more normalized, and then the scaling factors are changed accordingly. Okay, so that is basically what is batch normalization, and that's a standard layer you can use in many of these uh, libraries. So what has been shown is that if you train using batch normalization, usually you end up with lower losses than if you don't use batch normalization for both training as well as validation. So these are for two different data sets. So one is accuracy, the other is loss. Sorry, not two different data sets, same data set, but one is loss, the other is accuracy. So accuracy is better, loss is lower for both, not just for training but also for validation. So both dropout and batch norm will help you uh, increase your the performance of your neural network, accuracy of your neural network. Yeah, so it's important to note that you are actually looking at one activation or one particular neuron, and you are normalizing for that neuron across the mini batch. Okay, it's not across the layer. You are not normalizing all neurons of a layer with respect to each other. You are normalizing all activations of a single neurons with respect to that neuron's activations. Okay, so could you explain batch normalization one more time? So let's look at here. Right. So let's say you have a particular neuron. Okay, there are other neurons also in this layer. So this neuron will give you one activation for, so there are different samples, right? One all the way up to, let's say your batch size is B, right? So there are B different samples, and B samples, and they are like different dimensions, X1 to XD. Okay, so this is for the first and this is for the last in the same batch. So now all of these are going through somewhere, and they are basically giving you this activation A1 all the way up to A capital B. Okay, they are giving you B different activations because they are all part of a mini batch. So it is batch normalization. For these activations, it could be that they are all very small, or they are tightly clustered, or they are like all close to zero, because of which this neuron is not sending any gradients back. Okay, so instead I want to force this neuron to send different gradients back for different inputs, inputs in the batch. So what I will take is what I'll do is I'll take this activations and I will renormalize them. Okay, and what I will say is that I have a different uh, I'm mapping them into into a new space where they are zero mean and unit variance, and based on that I will compute the gradients and I will send them back. Okay. So that basically, if they were too large, if the gradients were too large for all of them, then also it is an insurance against that. If they were too small, then also it's an insurance against that.
So you're normalizing for a given layer, right? Like activations coming from a given layer across all samples in the mini batch.
Yeah, Yeah. Okay. So this is the end of the lecture. Any questions?
There's a chat question.
Ashish?
Sir, my question is that these, if there are going to be assignments for these things, batch normalization and dropout, probably to implement them from scratch or something. So, I mean, do we have to do it by using NumPy or something, or we can do it with like using something like TensorFlow or PyTorch? Like,
Yeah, I think these are using TensorFlow or PyTorch. Oh, sorry, mostly TensorFlow.
I mean, just implementing them from scratch. Things are a little different with how
Yeah.
PyTorch and TensorFlow works.
Right.
I'm not
Right.
talking about Keras. I'm just talking about the basic building blocks.
Yeah. Yeah. Yeah.
Yeah. So we can do like whatever is fine.
Yeah. Yeah. Let me see. I have the assignment statement with me. Let me see. So it's ready. I'm actually not too familiar. Saqib Shamsi is the one who brought this assignment. So we will be releasing this. I think. Let me see where the batch norm part is, whether it's from scratch or not. So it's actually quite an extensive assignment, and we'll give you extra time for this. Yeah, I think a lot of it is from scratch, unfortunately. So, but that's a good way to learn. Your concepts will be crystal clear. In fact, if you take any other course worth its salt, right? So there has to be at least one assignment where you implement it from scratch. Okay. Any other questions? So Pratigya has a question. So is it like for a given data, we are building multiple neural networks? That's why we are using batch normalization. So, so that multiple neural networks concept was for dropout. I wouldn't necessarily mix the two concepts. You can have batch normalization and dropout in the same network, but I like conceptually I wouldn't mix the two. I don't know if anyone has analyzed the two. So the multiple neural network effect was for dropout, not for batch normalization. Any other questions? Okay. So shall we call it a day then? All right. Thanks everyone. And thanks JD for pitching in.
Sure.
Okay.